So this section is about exponents and the scientific notation. Now this is going to go fast. I'm going to suggest more detailed videos if this is something you really are not good at, like working with exponents. But here what I have is a list of all those rules. So in the videos they're explained. It's explained where the rules are coming from. So I've got a list of rules. Some of them have names, like the product rule, the quotient rule, the power rule. And on the right here column, I'm going to show you some examples. So the product rule, so what is that? Well, it says, for example, if you've got 2 to the 3, so that's like 3 copies of 2, like almost like multiplied together, and then 4 copies of 2, overall you've got 7 copies of 2, right? You add up the exponents to get how many 2's you have, okay? Quotient rule works almost the same. You've got, let's say, 3 copies of 2 at the top divided by 4 copies of 2, right? This is like 2 times 2 times 2 divided by 2 times 2 times 2 times 2. So every time you've got a 2, right, 2 over 2 is equal to 1, right? You could actually write this as 2 over 2 times 2 over 2 times 2 over 2 times 1 over 2. So basically all those, well, you can forget about them because this is 1 times 1 times 1, okay? So you're just left with a 1/2. So you're left with a 1/2 because of the quotient rule, where you actually do 3 minus 4, you get 2 to the minus 1. And 2 to the minus 1 is actually the same, and this is a rule we're going to see below. It's the same as 1/2. Okay. Now the next rule is a to the 0 is always 1. So if you've got, let's say, 3 to the 0, this is 1. Okay, so this is not something that we decided. It actually follows from the product rule. So it's all explained also in a video from the previous course if you're interested. But otherwise, you can just accept it. 3 to the 0 is 1. If you've got 7 to the 0, that's also 1. A to the minus n is 1 over a to the n. So actually I already applied this right there. But, you know, I could say 3 to the minus 4, that's 1 over 3 to the 4. Okay. Then there's a power rule. So if you've got 2 to the 4 to the 3, you can write that as a single power of 2 by multiplying the 4 and the 2. And the reason is that if you've got 2 to the 4 to the 3, you've got what? 2 to 2, that's 2 to the 4, but that's raised to the power 3, so it's repeated 3 times like that, right? So overall, you've got 3 times 4 copies of 2, so you've got 12, right? You can actually see it. So this is 2 to the 4 times 3, so 2 to the 12. Okay. So you have to know these two pretty well, right? Sometimes they get confused. This one and this one, the power rule and the product rule. Sometimes people don't know when they add and when they multiply exponents. So make sure you understand this. And of course, this also shows you if you can multiply the other way around, right? 3 times 4, and then you can invert the power rule and write this as 2 to the 3, 2 to the 4. So this is how we see that a to the m to the n, that's the same as a to the n to the m, right? You can actually switch those two around and it doesn't change the result. What else is there? Okay, let me okay, so here we are here now. Okay. Well, actually we're more here. A to the b to the n is a to the n times b to the n. So for example, if you've got 2x to the 3, well, that's the same as 2 to the 3 x cubed. So that's 8x cubed, like that. And you've got something similar if you've got fractions. So if I've got, I don't know, 2x over 3y squared cube, well, that's 2x cubed over 3y squared cube. And I can keep going like this. Now I can apply my power rule above. That's 2 to the 3x cubed over 3, and apply the power rule below. Y squared cubed. No, that's not applying the power rule. That's applying the previous rule. The rule a b to the n is a to the n, b to the n. But now we can apply the power rule for y squared cubed. So that's 8x cubed. 3 cubed is 27. And y squared cubed is y to the 6. Okay, so I've applied many rules here. But the first one I've used, right, was this one, the last rule that was on the list. Okay, that's the one I used right there. Okay. After that, here I've used this rule, and after that, right there, for this, I've used the power rule. Now, a popular type of exercise to practice all these rules is you're given a very complicated expression with exponents, and you want to rewrite it so that it does not contain any negative exponents. Because negative exponents are fractions, right? So if I have something to the minus 2, it's 1 over something to the 2. So by not having negative exponents, we're making sure that there aren't any fractions anywhere. So usually with something like this, you try to first, if you've got like a fraction, you see we have got a fraction inside here. Let's try to rewrite this without, or well, regroup our x's together, our y together, okay, and simplify this, and then we can raise everything to the power minus 2. Okay, so 18, well, 18, I recognize that in 18 there are factors of 3 maybe that can cancel with what appears at in the denominator. So I'm going to write my 18 as 2 times 9 and 9 as 3 squared. Okay, so this way I can maybe simplify the 3's together. Now x squared I'll keep like that. Y to the 0, that's 1. Okay, so this is just 1, so I'm gonna essentially ignore it. Z to the minus 3, and below I've got 3 to the 4. 1 over x, that's x to the minus 1, and y squared. So I'm gonna try to regroup exponents, powers with the same base. Okay, so not exponent, powers. So 2, there's no powers of 2, but 3 squared, 3 to the 4, so that's 3 to the 2 minus 4, according to my quotient rule. X, I've got x squared, and x to the minus 1 below, so that's 2 minus 1. Okay, and that's z to the minus 3, I'll just keep it there, y squared, and there's, yeah, that's good. Okay, I thought there was an extra power of 3 left, but no, I took care of that. So, okay, let's perform the subtraction. So this is 2 times 3 to the minus 2. Of course, you can do this. You can skip the previous step. I just wrote 2 minus 4 so that you could see where the minus 2 is coming from here in the power of 2. And then x to the 3. So once again, like, you can handle the x squared and the x minus 1 directly and write that this is x cubed. Okay, so this is a step you can definitely skip. It's just I did it so that you could see where my numbers were coming from. Z to the minus 3, and finally y squared. Okay, now everything is raised to the power minus 2. So essentially it's going to hit everything in the denominator and everything in the denominator. So in other words, it's going to be like 3 to the minus 2, x squared, z to the minus 3 raised to the power minus 2, and y squared raised to the power minus 2. And then if you raise something to the minus 2 and there's a product inside, okay, the power, the exponent basically distributes and becomes an exponent for every factor in the product. So 2 to the minus 2, 3 to the minus 2 times 2, right? I'm applying essentially the power rule here. So minus 2 times minus 2 is 4. X to the minus 3 times minus 2, minus 6. Z to the 6 over y to the minus 4, like that. And now I've got negative exponents, but I know how to handle those using this rule right here, okay? So if you've got a negative exponent in the numerator, you can send it down in the denominator and change its sign. And same goes if you've got a to the n, okay, it's 1 over a to the minus n. So if n is negative here, by sending it, well, actually, let me well, this is kind of correct what I was about to say, but let me rephrase that. If you've got a to the minus, okay, actually, let's rewrite it this way. If you've got a to the minus n, like so, a negative integer for an exponent in the denominator, if you bring it up, now it becomes a positive integer. Okay, so here, everything that has a negative exponent in the numerator, I'm going to send it down, and now the exponent is going to change sign. So whenever if you send it down or up, the exponent changes sign. That's basically the moral of the story here. X to the 6 and no, y, I want to go bring it up. So 3 to the 4, y to the 4, z to the 6, like this. And maybe finally 3 to the 4, that's 81, y to the 4, z to the 6 over 4, x to the 6. And that's our final answer. And as you can see, there are no negative exponents, which means no fraction. For example, if I'm stuck with it, let's say if I've got a minus 6, that z to the minus 6, that's actually would be 1 over z to the 6, okay? So that there would be a fraction. So that's why we don't want to have negative powers. We want to write our answer without having what's called a complex fraction. I want a fraction within my fraction, okay? So what else is there now? In terms of exponents, we've got x to the 1/2. That's a notation for the square root of x. Again, the reason why it's 1/2 stands in the exponent stands for a square root. Comes from the product rule, really, because if you do x to the 1/2 times x to the 1/2 and you apply your product rule, you get x to the 1/2 plus a half. So you get x to the 1, so you get x. So the number that gives you x that you multiply by itself to give you x is the square root of x. So that's why this is square root of x here. So this is a quick explanation, but this is really where it comes from. And x to the 1/3, applying the same principle, that's actually the cubic root. And you've got the same thing, 1/4 would be the 4th root, but usually we are not going to deal with roots that are higher, well, nothing higher than the the cubic root. For example, if you've got a to the 7/3, okay, well, first of all, you can think of that as a to the 7 raised to the 1/3, right? You can also see it as a to the 1/3 raised to the power 7, right? Remember, by using our power rule, we can multiply the exponents. We're going to get 7/3 either way, okay? But like, which one should we use here? Well, it depends if we think it's going to be easier to do a to the 7 or a to the 1/3 first. Okay, it depends. Now, 8, what is that? 8, that's 2 times 2 times 2. It's actually a perfect cube. Okay? So the cubic root of 8, okay, which is what a to the 1/3 is, okay, that's actually 2. Okay, oh, so this is actually easy to do. So I should actually use this one, okay, because a to the 1/3 is 2, and essentially that's 2 to the 7. So I've sort of simplified that a to the 7/3, okay. Finally, scientific notation. Okay, sometimes in science we've got pretty large numbers. That's like not even a large number. Okay, that could be the, well, that's a little less than the population of the great Montreal area. But when we've got numbers like this with a lot of digits, okay, often we want to write it in a way so that it's a number between 1 and 10 that appears here. that's multiplied by a power of 10. Okay, so here the period is here, and you can move it by 6 like this, six steps to the left, and get 2.870418. Okay, but to make things equal, if we've moved it, move the period 6 times, the decimal 6 times, we've divided essentially by doing that. We've divided by 10 to the minus 6. Okay, so if we want to make things equal, we need to remultiply by 10 to the 6. So this is how what you see on the left is equal to what you see on the right. So careful here, right? This is a period right there, and this is actually a multiplication sign, so maybe it's easier if I use like the cross here, just for once. Okay, so this is writing this number in decimal in scientific notation. You could do the same with numbers that actually less than 1, like let's say 0.00182. What we want to do now here is move the period 1, 2, 3 steps like this. Okay, so we're going to do 1.82, and here we've multiplied by 10 to the 3. So to make things equal, we need to multiply by 10 to the minus 3 too. Okay, so that's 1.82 times 10 to the minus 3. You could have also negative numbers, minus 2.4 times, can you guess what it's going to be? 10 to the minus 2. Okay, and in general, number in scientific notations of the form a times 10 to the n. N is an integer, and a is such that it's a number whose magnitude is between 1 and 10. What's the magnitude of the number? It's the absolute value, or it's the number itself if it's positive, and its opposite if it's negative. Okay, so the magnitude of, for example, minus 1.85, that's 1.8584. That's 1.84. Okay, that's the magnitude of the number. It's the distance of that number to 0. Okay, so it's very practical, this scientific notation, if you're working with large numbers, or large and small at the same time, especially in physics and chemistry. You've got like these very big numbers to work with. So for instance, right, you've got H2O water that has 3 atoms, right, 2 hydrogen, 1 oxygen. A drop of water has actually 1.32 times 10 to the 21 molecules of water. That's a lot. 1 liter of water has 1.22 times 10 to the 4 drops. And let's say you want to find how many atoms are in one liter of water. What you don't want to do is start converting those numbers, like, okay, and say, okay, 10 to the 21, it would be 1, 3, 2, and then you'd have to add like 19 zeros. So that's crazy, right? You don't want to write that number and start multiplying it with 1.220, that would be 12,200, and multiply the numbers together. No, that's crazy. What's a lot easier to do is to use those numbers in scientific notation. So if I want to find how many atoms of water there are per liters, right? What do? Well, I've got 3 atoms per molecule. And then how many molecules per drop? Well, 1.32 times 10 to the 21 molecules per drop. And then how many drops per liter? I've got 1.22 times 10 to the 4 drops per liter. And then you can see the drop, right? That cancels, that cancels, that cancels. Overall, I'm going to get atoms per liter. And if you multiply, you could multiply these together. Okay, that's way easier, right? Those are easy numbers to work with. I'm going to get 4.83 approximately. And if you multiply your 10 to the 21 and 10 to the 4, you just have exponents, powers of 10 to multiply, and you add the exponents, you're going to get 10 to the 25, and you've got your number in scientific notation, and it's a lot easier to work with that.